Welcome to the sixth Introduction to Geometry lecture. The topics that we will explore in this lecture include the 3x3 matrix form for conics, a test for degenerate conics, and quadric surfaces. Okay, so we'll start this lecture with the exercises from the previous lecture. So the first equation is x squared plus y squared is equal to 0. We've seen this equation before. We know that this is a single point, a degenerate conic. But let's look at the matrix A. The A term is 1, the C term is 1, and we have no B term. And the determinant of A is 1 minus 0, which is 1, which is positive. Now, the classification theorem that we had in the previous lecture said that if we have a non-degenerate conic and the determinant is positive, then we have an ellipse. Well, here we have a degenerate ellipse. When an ellipse degenerates, it contracts to a point. So the second equation we'll look at is x squared minus 2xy plus y squared is equal to 0. We've also seen this equation before. It is a single line, y equals x. That is doubled. That is, it's the square of the term x minus y. And so we have the line twice, the line y equals x. And if we look at the matrix A, in this case, then the A term is 1, half of the B term is negative 1, and the C term is 1. And so the determinant of this matrix is 1 minus 1, which is 0. And again, the classification from the previous theorem tells us that if we have a non-degenerate conic and the determinant is of the matrix A in its quadratic form is 0, then we have a parabola. And here we have a degenerate parabola. The parabola collapses to a single line, the line y equals x. And now the third equation is the equation y squared minus x squared is equal to 0. We've seen this equation before as well. This is two intersecting lines, the lines y equals x and the y equals negative x. And so this is a degenerate conic as well. If we look at the matrix A, then we have the A term is negative 1, and the C term is 1. There is no B term. And so the determinant of this matrix is negative 1 minus 0, which is negative 1, which is less than 0. And our classification theorem tells us that if we have a non-degenerate conic, then the determinant of the matrix A in its quadratic form, if it is negative, then we have a hyperbola. So here we have a degenerate hyperbola. The hyperbola straightens to two intersecting lines, the line y equals x and y equals negative x. So what do these equations have in common? What is the telltale sign that these are degenerate conics? And the answer is that each one is reducible in the field of complex numbers. That is, each of these equations can be factored into linear terms in the field of complex numbers. So we'll start with the first equation, x squared plus y squared. This can be factored in the complex field as x squared plus I times, x times I plus y times the quantity x minus I times y. And in the real plane, this manifests as a single point, the point 0, 0. And if we look at the equation x squared minus 2xy plus y squared, as we've already seen, this is a repeated linear factor, x minus y times x minus y. And in the real plane, this manifests as the single line y equals x. And the third equation is y squared minus x squared. This is a difference of squares, and so we have y minus x, y plus x as the factorization, and this manifests in the plane as two intersecting lines, the lines y equals plus or minus x. So we can determine, or identify rather, that a conic is degenerate based on whether it can be factored into linear terms in the complex field. And the easiest way to do that is to work with a matrix. And so we will now look at a 3 by 3 matrix. So consider the conic E with the equation ax squared plus bxy plus cy squared plus fx plus gy plus h is equal to 0. Let the vector x be the vector x, y, 1, so a 3 by 1 vector, and let the matrix M be the matrix A, B by 2, F by 2 in this first row, B by 2, C, G by 2 as the second row, F by 2, G by 2, and H as the third row. Then the matrix equation, the transpose of the vector x times the matrix M times the vector x is equal to 0, is the 3 by 3 matrix form for the conic E. So let's, as a theorem, let the equation x transpose times M times x equal to 0 be the 3 by 3 matrix form of the conic E with equation ax squared plus bxy plus cy squared plus fx plus gy plus h is equal to 0 if the determinant of the matrix M is 0, then the conic E is degenerate. So proof. Since the matrix M is a real symmetric matrix, it is diagonalizable and so the matrix M is similar to a diagonal matrix D, and hence there exists an invertible matrix P such that The inverse of P times M times P is the diagonal matrix D. Further, the elements or the entries of the diagonal matrix D are the eigenvalues corresponding, respectively, to the eigenvectors in the matrix P. So we have P inverse times the matrix M times the matrix P is the diagonal matrix D, that's whose entries are the eigenvalues, which we'll label as lambda 1, lambda 2, and lambda 3, corresponding respectively to the eigenvectors in P. And so P inverse and P act to transform the equation, or the coordinates rather, for the conic. So the transformed equation for the conic E is lambda 1 times x prime squared plus lambda 2 times y prime squared plus lambda 3 times z prime squared is equal to 0. Now recall that in a 2 by 2 matrix, a 2 by 2 matrix represents a transformation in the plane, but a 3 by 3 matrix represents a transformation in three-dimensional space. And so the transformation for the matrix, or for the equation for the conic E using a 3 by 3 matrix is in three-dimensional space. And so that's why we have x prime squared, y prime squared, and z prime squared. Now, since the matrix M is similar to the matrix D, the determinant of the matrix M is equal to the determinant of the matrix D, which is the product of its eigenvalues, or the eigenvalues, lambda 1 times lambda 2 times lambda 3. So if the determinant of M is 0, then at least one eigenvalue is 0. So let's look at two cases. Case 1, exactly one eigenvalue is 0. And without loss of generality, we will assume that lambda 3 is the is the value 0. Then the transformed equation of the conic E is lambda 1 times x prime squared plus lambda 2 times y prime squared is equal to 0. Now if lambda 1 and lambda 2 have the same sign, Then lambda 1 times x prime squared plus lambda 2 times y prime squared is of the form a squared times x prime squared plus b squared times y prime squared, which can be factored into linear terms in the complex field as a times x minus I times b times y and a times x plus I times b times y. And so this is a single point, or the equation of a single point. Now if lambda 1 and lambda 2 have opposite signs, then the equation, the transformed equation of the conic E is either of the form ax prime squared minus, a squared x prime squared minus b squared y prime squared is equal to 0, or we could have b squared y prime squared minus a squared x prime squared is equal to 0. In either case, we have the linear factorization. Well, in the first case, we have the linear subcase, we have the linear factorization ax prime plus by prime times the quantity ax prime minus by prime. And so this is the equation for two intersecting lines. And in the second equation, we have, that should be b squared. And so we have b times y prime minus a times x prime times the quantity b times y prime plus a times x prime is equal to 0. In either both of these equations are intersecting lines. So case 2, two of the eigenvalues are 0. And without loss of generality, assume that lambda 2 and lambda 3 are both 0. Then the transformed equation of the conic E is lambda 1 times x prime squared is equal to 0, which simplifies to x prime squared equals 0, which is the line x prime equals 0 repeated or doubled. So in either case, if the determinant of m is 0, then the conic E is a degenerate conic.